you first find all of the gadgets that allow you to assign the targets on the left-hand side. Then for each of these gadgets that you have enumerated, you verify that the constraints that at this point have to hold really do hold by converting the gadgets into STP formula, triggering STP, and then if it tells you this is not satisfiable, you just scratch it off the list. Then you go to the right-hand side of your expression, and you do the same thing, but of course there you have to build the expressions and you have to chain the gadgets, so you go from inside out, and you incrementally build this and you get more and more complicated STP formula. Obviously, for each of these steps you have multiple gadgets potentially that you can use. So you have kind of a recursive procedure where you throw out the gadgets that cannot be used in each recursion step. Now, when you're done with that and you have the left-hand side and the right-hand side, you connect those two. Again, you have to verify that the constraints do hold. Obviously, if it's just a constant assignment that you do, that's trivial. So you don't have to do anything in the component on the right-hand side. It's just the left-hand side that you consider there. Now, you may ask yourself, why do we have this multi-assignment? So the reason for that is that we wanted the compiler to have flexibility. So what actually happens is that you can perform these multi-assignments in different orders. And the order is randomly chosen. If this order cannot be, if like a ROP shellcode for this order cannot be built, what the compiler does is it just chooses another permutation of the assignments and triggers the procedure again. So why is that necessary? So for instance, you may have the case that you always have gadgets that whenever they compute an addition into the register R0, clobber the value R1. On the other hand, you need to assign the value, the register R1 to a value. So the programmer goes and, if you didn't have a multi-assignment, first assigned this, R1 and then R0. Then this couldn't be satisfied. With multi-assignments, you can give the compiler the freedom to choose this for you, basically. Okay, so some notes on the chaining algorithm that we use at the moment. So it obviously will use registers, but also memory locations as scratch for temporary results. The multi-assignments give us the freedom that we need. So without the multi-assignments, some of the demo programs that we have actually would not compile with the gadget sets that we have. But also, it is possible that the algorithm will fail, or let me put this a little bit more mildly, it will tell you that the program cannot be compiled as you've written it because the gadget set is insufficient. So this can actually be solved in a number of cases. One of them is for you to rewrite the program then, and maybe it works in a different way. The other way that we could explore here is to have a term rewriting system that transforms some of the equivalent statements that you can have. For instance, if you have a multiplication by 2, you could just as well transform it into an addition of the same value. But we have not done that part yet. Okay, so I will now hand over to Vincenzo, who will tell you about how to test the payload.
Okay, so Tim and Ralph have shown you how to basically create the payload by first finding the gadgets and then chaining them together. So now let's say that you have your payload and you are still targeting the iPhone. There is the problem of testing the payload. So one can think that testing the payload on a jailbroken phone might be an option, but in reality it's not. Because first off, basically on the jailbroken phone, you have no code signing. So a jailbroken phone is not like a non-jailbroken phone. So if reliability is your primary concern, then you should avoid testing your payload on a jailbroken phone. On the other hand, you can use a debugger on a jailbroken phone like GDB, whereas on a non-jailbroken phone, this turns out to be impossible. So another way you can go about it is to use a developer phone. So basically, it's a phone enabled with a developer certificate. So the idea is pretty simple. You have a simple test application that tries to reproduce a return-oriented programming scenario. And there's still a problem, though. The problem is that the sandboxing policy for the testing application will be the strictest one you can find on the iPhone. Because I forgot to mention this at the beginning, but basically on an iPhone, you have different sandbox policies depending on the application. So the App Store application are the one with the strictest sandboxing policy, but it's very likely that you are instead targeting some other type of application like Mail, Safari, or even some daemons which have either a different sandboxing policy, or in some cases they don't have a sandbox at all. So still with a developer phone, you can try to verify whether or not your payload is correct, but probably the kind of thing you can do with your payload really depends on the target application. So, but anyway, this is like the closest you can get to reality. And also, if you have a developer phone, you can use the Xcode debugger to try to get some more information about the payload itself. Because otherwise, like what we had to do for Pwn2On was debugging the payload using the crash log from iTunes, which is really not fun. So, the plan for testing application is really simple. So you basically allocate a buffer on the heap. You put your shellcode inside this buffer on the heap, and then make sure that the stack pointer points to the attacker control buffer, and you basically execute the payload and restore the execution so you can try it multiple times. And now we're going to show you a simple demo about on testing a payload on a developer phone, and then we will discuss briefly the future plans that we have for return-oriented programming. Okay, thanks. Okay, so we're going to show actually two different things. The first thing is a payload. Well, sorry, a payload like the same payload we use for Pwn2On, but written in the language that Ralf created for our compiler. So, Ralf, do you want to briefly explain it, or shall I do it? Okay. So basically, like the payload was a file stealer payload. Was really simple. You have to basically open the file that you want to steal, then create a connection to a remote host and send over the file. So as you can see here, we are basically able both to call library functions and do other kind of operation as well. So first, like we are opening the function, we pass the arguments to open. We call the function, and then we make sure that the return value of open is protected, so it's not overwritten by other gadgets. And then we call socket, and once again we are protecting the return values of socket, and we connect to the remote attacker controlled host, and here we are mapping the file on in memory, and then we basically send the file to the attacker, and here we are sending the file to the attacker, and then we basically shut down the process. So so this is like the point of this demo is to show that it's actually feasible to write like complex payload using the language that Mr. Wolf understands. So for a problem with the sandboxing policy, being that our our testing application runs with the sandboxing policy of an App Store binary, we are not going to show you this payload, but we will show you a simple vibrate payload. So. So let me just create a network for the phone. Okay. So basically what we will do now is to use our test application to make sure that this payload actually is correct. Is actually correct. So this payload is really simple. It's basically just call a function called audio services play system sound that basically make sure will make sure that your phone vibrates, and then it will exit, and that's pretty much it. And so this payload compiled looks like this. Okay, so like something like this, and now can't remember. Okay. Let me just. Sorry, I forgot to connect the iPhone to the test network before. Okay, it's acquiring this IP address. Okay, so okay. So we run on the iPhone the test application, and now if everything goes according to the plan, can you hear it? Okay. So this is basically how we test the payloads, and so enough with the demos. The future work. Okay. The future work. So, as Tim said, at the moment, the algorithm for finding gadgets is really dependent on the compiler and on the platform. What we are planning to do is to port port the gadget, like the gadget finder, to other architecture like x86, so that it's possible to use this